Okay, welcome for the afternoon panel discussion. Today the panel is about S-matrix approaches, yes or no. Our panelists today are Emil, Bjerrum-Bohr from Niels Bohr Institute, Mariana, Carrillo, González, Imperial College, Dvali, MPI Munich, Arkady, Tseytlin, Imperial College also, and Richard, Woodard, Florida. As customary in this panel discussions, I've learned after first very brief remarks about what the topic is about, I leave the floor to our panelists who will introduce some of their remarks. And after that, we will continue with discussions from the public. So please make it interactive as much as possible. And so I think let's start. Well, so do we really have to answer the question yes or no? S-matrix is definitely one of our main tools in understanding and formulating fundamental interactions. Amplitude computations are really the basis for any of our connection from the theory to reality. That's what we need to test our interactions. And moreover, coming up with gravitational wave experiments, the applications of these frameworks to gravity seems natural. They are useful background to implement some constraints that may have, they're not perturbative, they have a fundamental origin, and we require all our theories to hold up to those. But they have some constraints. For example, we need to have a definition of symptotic states. Our approach applies whenever we are in a regime where there are symptotic states. And if we want to go beyond the pure perturbative analysis, well, there's interesting attempts and progress, but we need to resort to some numerical methods. So you can see there's actually a lot that behind simply applying S-matrix approaches or formulating. So I know some panelists have prepared some of their remarks in the slides that I will show right after, but I think that they all agree that there's some questions, and if you want, I can put them up later. But on the gravitational part, can we really reconstruct our metric from the S-matrix? How far can we push it? In what regimes can we do it more easily or less easily? Comments on analytic versus numerical approaches. Do we have to prefer one of them? Should we pursue both at the same time with the same efforts? Do you think there's this is a powerful approach that you would invest your research on, or do you think it's too limited and you have a favorite approach that goes beyond that? And if you agree with the power of S-matrix, do you think we can really at some point find some interesting discovery about our understanding of gravity from S-matrix approaches? And definitely, please comment on what you think is gonna come next. So I'm gonna now leave the floor to the panelists. We can start in alphabetical order, in sitting order, whatever you prefer.
You're the leader.
So I have put them in alphabetical order.
Go for it. Okay.
So let's please start with Emil.
Yeah. So I just wrote some quick comments, but I think
you can look at this if you want to.
it aligns very much with what you were saying. So I think we need to have quantum gravity that connects to the known low energy physics, and that being PR predictions, EFT, PR predictions. So that would be a yes. I mean, I don't see why we should avoid having that. I mean, then it's unclear, at least to me, what we're talking about. If we have low energy consequences of an S-matrix theory, we can use that to drive theoretical research forward, because we can try to see which models can give the same and how we can modify. And as you said, gravitational waves, we have observations. We have to connect quantum gravity and classical limits to those observations. And if we build models, it's easy to do that in the context of an S-matrix approach, where we have full control of what states we put in and how interactions are. And consequences we can then analyze in the context of decision or measurements, things like that. So it would be 3 yeses from here.
Same, yeah. Yeah, you're done.
I'm done.
Yeah.
Who's that?
I think it's Mariana alphabetically. I can move
Yeah.
that slide.
Yeah, I have yeses, nos, and maybes. So the obvious ones, yes, we know we need it for colliders, we know we need it for tabletop experiments. Wherever you have flat space approximations that work, S matrix is amazing. We know also, as we've seen from these talks, that you can do generation of gravitational waves, you can approximate this as flat space, and you can get it. But there's just one thing I wanted to point out. Scattering in with the S matrix is a scattering process. So you're not really having the kinematics of having a bound state, you're actually scattering two black holes. And the waveforms from these two processes are quite different. If you're just having what's called a hyperbolic encounter, you have the two black holes, they scatter out, and the waveform is sort of oblique. They're really hard to detect because of that. The one that is thin spiral that we've been detecting is many oscillations, as you all know, and that's why it's easier to detect. You have more data. Now, the question is, can you infer from the scattering the one that is the bounded case? And the answer is yes in many cases, and people know this. But as far as I know, there's one case where you cannot do it, and we have experts here that can tell me if there has been any development and now actually being able to do this, and it's when you have tail effects. So when you have the gravitational wave in spiral, you're gonna radiate some gravitons, you're gonna lose energy in your system, but also these radiated gravitons can scatter back, and this will also again change the dynamics of your inspiral. So this is gonna be a non-local in time effect. And these non-local in time effects, people don't know how to translate from this system of scattering to a bounded system. So the S matrix approach, when you actually want to compute tail effects, which start at order d to the 4, they don't really give you a bounded system, they give you a scattering system. So unless you have a way to translate this, and we know how to translate this in certain cases, as I said, some reasons are because of integrability, they only depend on conserved charges. Beyond that, we don't really know. So just the Newtonian case is just an integrable system, it just depends on the conserved charges. So what you're translating is just boundary data. When it's a curved black hole in the probe particle limit is the same. Beyond that, we don't exactly know why it works, but we know it can be done. But these tail effects, not really. Non-local in time, not really. So I would say S matrix for those is not one. Another no, I think it's another obvious thing, which is curved spacetimes that don't have S matrices. It's very obvious, you don't have this matrix, so you cannot use it. But I also would say there's no need for it. Sometimes it's phrased as a bad thing to not have an S matrix in a curved spacetime, but I don't think it's a bad thing. We have cosmology, we know how to do observations, we have other observables, we know how to compute correlation functions. We can just go compute these correlation functions from whatever early universe theory, inflationary theory that you want. We know how to evolve them, we know how to measure power spectra with the CMB, translate this to overdensities of matter, to galaxies, whatever. We have measurements, we know how to do this, and there's no need for an S matrix. So I would say in those cases, we don't need it. There's also propagation of gravitational waves. This you actually need the expansion of the universe. You don't need an S matrix approach for that. And what I would say a maybe is, again, the gravitational waves. If you find a dictionary for all the cases, including the tails, maybe there's hope and maybe you can use this for those cases. Maybe when you do cosmology, so I know there's attempts to define an S matrix in those cases. I don't see a use for phenomenology, but if you want to define an S matrix and you know analyticity properties there, and you can find positivity bounds for your theories, so from a theoretical perspective, it might be useful. And I will just say, I don't know if there are other lessons that you can learn from these or new observables, perhaps, so I will just leave those as questions.
Thank you very much. Let's move on to, I think it's in alphabetical order.
Yeah.
I'll put it on a neutral slide. So.
Okay, so there are two things I want to differentiate. I want to differentiate the necessity for the formulation of the theory from the computational tool. So the S matrix is currently I don't know any other formulation of quantum gravity. If we define quantum gravity as a theory of massless spin 2, in particular in string theory, this is completely organic, but goes beyond. And the reason, okay, so I will not enter into the reasons, but okay, partially the fundamental reason is black holes, because since scattering in gravity is dominated by black holes in deep ultraviolet, and black holes become bigger and bigger, if you want to scatter, if you want to define your theory, I'm not talking about computation, to define your theory at arbitrarily high center of mass energies, then you have to deal with arbitrarily large black holes. And so asymptotic, you need asymptotic states, and you need globally defined time. So therefore, now, what are the benefits from this? Now, the benefits are that since S matrix is directly sensitive to the vacuum of your theory, it puts very important constraints on the vacuum of your theory. And we like to be constrained, because that's what physics is about, to constrain our theories and make predictions. So, for example, in particular, the Sitter space in string theory is non-existent because of that, because you cannot define S matrix on such a background. Now, so the people talk about background independent formulation of gravity in string theory, and this in particular in string theory, and this was considered to be one of the questions. My philosophy is different. Actually, it's opposite, because if fundamental theory is background dependent, that's a fantastic thing, because we want fundamental theory to be restrictive. Take Einstein gravity. In Einstein gravity, every background is a vacuum. You can use it as a vacuum for small fluctuations. You can use background, arbitrary background. So from the point of view of Einstein gravity, there is no difference if you are in the Sitter space or you are in Minkowski space. It's just, they are both backgrounds, they're perfectly fine. But the fundamental theory, the whole point of fundamental theory is that it has to be more restrictive. And so not every background of Einstein gravity should be a valid vacuum or even a background in fundamental theory. And that's the great thing, and this is what string theory is telling us, that there is no de Sitter vacuum, there's no eternal inflation in string theory that we can get. And this is a fantastic thing. So we get predictions from there. Also, I mean, the fact that literally every aspect of the theory that is sensitive to the vacuum structure is restricted. For example, theta vacua immediately are restricted. Basically, the S matrix for any quantum gravity which is formulated on the S matrix tells you that the theta vacua have to be removed by axiom by chiral quarks, which is the same thing. And again, finally, I want to reiterate that we have to differentiate. Nobody is telling us that if we formulate theory through the S matrix, you have to do all the computations through the S matrix. Of course, that's obviously you can do computations. There are much more useful methods to do computation. This is about formulation of the theory. Okay, so now once the theory is formulated and the restrictions are met, that so certain vacua are eliminated from this theory, then you can go ahead and do computations as you like. And of course, in many cases, you can even solve classical equations of motion. That's much simpler than to do scattering problem. So not every aspect of our life, for example, our presence in this room, probably you can understand as some kind of very complicated S matrix coming from the future past, and then we got formed, and then we're gonna decay in the infinite future. But I mean, well, not infinite future, probably before, but we're not gonna right. But you're not gonna solve psychology of people in this room using S matrix. It doesn't make any sense. So the similar thing. Yeah, so that's what I wanted to say.
Thank you very much.
Okay, I just maybe a few obvious comments that its matrix framework was very successful in some cases, and maybe not so much in, say, for example, some primary PCDs don't formulate this matrix. So you need to know your spectrum, you need to know your vacuum. So this matrix depends on the choice of vacuum. Again, Higgs mechanism, how you discover it starting with trivial vacuum. Probably not if you just stay with this matrix, it would be not very productive. So one needs to be aware of that limitation, that we are sitting in a particular vacuum. Of course, you can say, okay, we live in this vacuum, that's we should forget about any other options. But if you just stay away from reality, just on theoretical grounds, this matrix is tailored to particular vacuum. But thinking of it as just tailored to flat vacuum is too limited. And the good perspective on that's goes back to 60s, but it was formulated clearly by, say, Arefьева, Slavnov, and Fadeev, that you can define this matrix by first computing effective action, then solving classical equations with particular boundary condition, particular asymptotic conditions on a given vacuum, and then you plug it into effective action, you're generating functional Floris matrix. You don't need to go through LSZ, etc. That's a kind of quick way to get this matrix, which generalizes to some other backgrounds like PP wave or whatever, to some cases where you have well-defined states, asymptotic states, and you switch off interaction. So that's a more general perspective, but it's still depending on your choice of vacuum. But there is a bigger question how you go from one vacuum to another. For that, you need some off-shell concept like effective action or something like that. And that, again, questions were asked by Dvali, et al., that just looking at the Einstein equation, you're always kind of on shell, how you go from one configuration, like dynamical configuration or evolution of black hole or something like that. You need a non-equilibrium situation like evaporation of black hole. Also, you would not describe just staring at the Einstein equation, even with some semi-classical stress tensor. Well, you need to go beyond that. Anyway, so there are obvious limitations. Though its matrix is very powerful, I would not subscribe to the idea. I guess Arkady Hamed is very famous for advocating this, that some hidden treasures in the world are hidden somewhere in this matrix. And if you understand geometry behind the loop integrals, which define as matrix, you somehow may discover something fundamental. It's probably not the case, but who knows? But so far, I don't see there more than technical progress and some interesting mathematics. But that's just because I have very little awareness of that approach. But anyway, so the good thing is that one remarkable thing about this is matrix as defined as essentially effective action value to some classical solution with given boundary conditions, that generalizes to the ADS. And remarkably, you discover that this matrix defined that way is kind of matching correlation function of boundary primary operators, a concept which is natural in CFT. So before idea CFT, one would never dream of that idea that you have CFT, okay. In CFT, you have well-defined concepts of primary operators with given dimensions, you compute their correlation functions, and that's what is constrained by all sorts of basic principles. But that, via idea CFT, is matched to precisely what is homologous matrix in ADS. That's quite remarkable. Again, there are some attempts to push this to extreme, like saying, why don't we do the same in de Sitter with some energy continuations, etc. That doesn't seem to be, maybe that's also possible, but probably I already mentioned that there are some concerns about that idea. And it's kind of following analogy too much beyond its applicability limits. But anyway, one needs to think about all possibilities. But the short answer is that this matrix is extremely useful, but it's certainly probably not everything which exists in the world.
Thank you very much for the perspective. Very broad, interesting. We are now going to the left of the panelists with slides. So if you need to look at that.
I'm excited to always be last. I'll take the point of view that it can't be used as a fundamental definition of quantum gravity. And that's for two reasons. First, as has been mentioned, it doesn't exist for dynamical quantum gravity on cosmological backgrounds. And second, on a physical point of view, it doesn't capture changes in the background and in the one particle spectrum. I do agree emphatically that an S matrix is very, very useful for describing scattering on flat space and on anti-de Sitter space. And I don't want to be dogmatic in my own negative views about S matrix theory. I don't actually have negative views about S matrix theory. I think quantum gravity is a very difficult problem, and we should all do what we can do to try and shed light on it. Yes, please. So let's deal with the first problem, which is cosmology. There's some math issues and some physics issues. The math issue is, as has already been mentioned, the absence of asymptotic early and late empty states. The universe began with an initial singularity, and even if you believe that some theory is going to prevent that from occurring, it's going to get so close to an initial singularity as not to make any difference. That's not asymptotically free vacuum in the distant past. And it seems to be evolving towards a locally de Sitter phase. Again, this is not the cosmological particle production that's happening in such a phase is the antithesis of emptiness. The physics issues are cosmological particle production. It precludes the existence of a late free vacuum state. So your late state is going to be full of particles that get produced by cosmological particle production. That's not a bad thing. That's actually our best hope for observing quantum gravity. I would say we already have observed quantum gravity, so that's a wonderful thing. But it does preclude using the S matrix as the way of defining quantum gravity. And secondly, causality precludes comparing asymptotically late measurements, right? An S matrix as technically defined entails that we observe all this stuff going off. We're putting some stuff in, interactions happen in some ways that we choose not to look at, and then stuff goes off. You could have the guys over here in the time that exists in the universe in the incoming phase compare notes and know what went in, but there is no way at all, if the universe is approaching a de Sitter phase, that the guys who are making these measurements there and there can ever compare notes. And so it's not an observable. There actually was an S matrix that was defined for a special theory for massive scalar fields on non-dynamical gravity by, Merolf, Morrison, and Gnecchi in 2012, I think. But even they admit it's not an observable the way that the S matrix is an observable in flat space. And I would say that these objections are crushing. The problem with extending an S matrix to cosmology is a crushing problem because the only quantum gravitational data that we have right now are cosmological. We're never, ever going to see loop corrections, perturbative loop corrections with any kind of a low energy accelerator that we can build. That's the biggest one that we can build right now that took all the nations of the world participating can get the loop counting, the dimensionless loop counting parameter, G times whatever's the characteristic energy squared, to be 10 to the minus 32. And we just can't measure that accurately, and we're not within anybody's lifetime here be able to measure that accuracy. On the other hand, we do have one data set that we've already observed at 3 significant figures, namely the scalar power spectrum. I'm quoting the amplitude for it. You can see that it's been measured. We have 10 to the 7th pixels of data on that. The simplest interpretation, there are always people with difficult points of view say, no, it could have been this or it could have been that. But the simplest interpretation of it is that it's the gravitational response to whatever drove inflation. I would argue that that makes it the first quantum gravitational, quantum fluctuations in whatever drove inflation. I would say that that makes it the first quantum gravitational data that's ever been taken. There's potentially enough data available in 21 centimeter radiation to look at the one loop correction to it, which would be like looking at the Lamb shift in QED, and every bit is significant, I think. There's also potentially a data set available in the tensor power spectrum, for which we only right now have an upper limit of 9 times 10 to the minus 11. That represents quantum fluctuations in gravitational radiation. And very significant, neither one of these is an S matrix elements. They're cosmological correlators. Second problem is that what an S matrix tells you is that there's no scattering between particle states in the theory. And that's precious information. And believe me, I'm not disparaging it. But there are other things that you'd like to know about, for example, the evolution of the background and what's happening in the one particle spectrum. So S equals 1 means that there's no scattering between states, but it doesn't preclude evolution of the background, and it doesn't preclude evolution of the one particle spectrum. And I'll not make this abstract. I'll give you an explicit example that, let's see, Chopin, who's here, and Samus and I cooked up in 2021 with some help from Arkady Tseytlin, a key realization from him. It's a nonlinear sigma model on de Sitter background. So it has two scalar fields, A and B, and it's set up, it's a typical nonlinear sigma model so that A is changing the canonical energy of B, or the canonical normalization of B. And Arkady pointed out to us that, in fact, there is a local invertible field redefinition, which makes this free. I've given it there. It's not even all that complicated, although we didn't see it. It's local invertible. So those of you who are a bit like me know that there's a theorem called Boelter's theorem, which says that that means that the S matrix is just 1. And so this theory would be dismissed as uninteresting if the S matrix is telling us everything that there is to know. But it isn't telling us everything that there is to know. This is on de Sitter background, and that's field A is, and field B too, also in free level or massless minimally coupled scalars. They experience inflationary particle production, the jitter that's caused by modes continually being dumped from the ultraviolet into the infrared. And that turns out to induce an effective potential. It's a kind of a funny effective potential. It's not one that you're used to coming from a field developing mass. It's coming from a field developing a field strength, but it still is an effective potential. I've given it there. It's a logarithmic effective potential. And for those of you who come from America and can't graph things anymore and figure out, that means that it opens downward. And that means that the field classically should just roll down. And indeed, that we had seen the roll down before we had derived the effective potential, which explains it. We had calculated at 1 and 2 loop order the roll down. We actually now have it to all orders. It's given by that. And it's that's the classical roll down that would occur in that effective potential. Of course, as I said, this theory is getting quantum jitter as well. And so there are stochastic fluctuations that occur there. But since it's easier to fluctuate down than up, the stochastic fluctuations are not going to stop the fact that it's rolling down. They're going to accelerate the fact that it rolls down. So this is a very, very reliable result. Notice, by the way, that evolution never stops in this theory. It's not wildly unstable or anything. It's a very sedate roll down, but evolution never stops. And the one particle mass also evolves. I've given an explicit formula for it. Again, we had confirmed this by explicit calculation at 1 loop order, stupidly by calculating the self-mass squared and looking at what happens, but you can see it much more easily this way. And I think those are interesting pieces of information, very precious information. They taught us how to sum up the leading large logarithms, which probably not most people know about, but they taught us how to sum up those things, and that was a wonderful piece of information. But the S matrix doesn't tell us those things. I would say that's a very, very strong case that you need to be open-minded and prepared to go beyond the S matrix. And that's it.
Okay, thank you very much. Maybe we can thank all the panel for the introduction. And I think we now open to everyone the discussion. Well, I can leave it on my naive questions or like key comments, or from the panelists if you have other remarks on your own.
Well, I think, I mean, nobody said that you should not go beyond the S matrix. So then, I mean, I trivially agree with what you said, but that doesn't mean that you can formulate
You
it
have a
here.
colleague, Charles Thorne, who's in the office right next to me. He says the S matrix is all you need.
No, this is a very story. It may be all you need for the questions that you are interested in, and that's fine. But
He's interested.
or he, whoever. But
People do say it, and pretty good physicists say it.
But I mean, who disagrees that there are methods that are much more efficient than the S matrix, or even the?
Well, I don't even think you can see it in the model that I gave. The S matrix is one.
So what? It's a very well defined S matrix. One is a fantastic.
But how do I see those pieces of?
What does that prove? I don't understand. So let's say S matrix.
So it isn't all you need. It isn't enough to tell us everything about the theory that we might
Of
want.
course, I trivially agree with that. I mean, that's obvious. I mean,
We agree.
And I think it's also one needs to look carefully at equivalence theorem, because indeed flat space is one thing, de Sitter is another thing, and yeah, there is a field redefinition, but whether you
That is an issue. I just assumed that Bohr's theorem applied to in general, and maybe that it doesn't apply outside of flat space. He was a
one needs to
physicist.
be essentially you are presenting
all kinds of
counterexamples.
things like uniqueness of the vacuum, and that the vacuum is the unique normalizable state, all of which cosmology makes sort of nonsense.
so this is a counterexample to what?
The equivalence theorem. Well,
equivalence
it started from equivalence theorem. You can do field redefinition, etc., but one needs to look at fine print sometimes.
But isn't the question also, if you say S matrix no, that's a problem. I mean, then you have a lot of things you can't describe, and you can't.
Well, I'm not saying that I thought I was careful. It can't be used to define quantum gravity. And I entirely agree with you using it to do awesome calculations, all of you. But let's by all means use every tool at our disposal to try and shed light on quantum gravity. It's beating up on our species pretty badly, right? We've got all the other forces.
And just on technical,
But that's how string theory is defined. So what's wrong with that definition? I mean, that's how string theory is defined. String theory is defined through the S matrix. There's not a formulation of the string theory.
Indeed, for the perturbative S matrix.
No, but S matrix per se has nothing to do with perturbability. S matrix would be that you can.
There's a non-perturbative definition.
well, we can also turn this around and say that this is deficiency. Because yes, that's absolutely true. That's how string theory is defined. You pick up a vacuum and you expand. But suppose you want to know what are the other vacuum. You need somehow to be able to see
Sure.
a framework which allows you
to
to see other
compare
vacuum.
them, right? Or compare different dimensional compactification.
Yeah, so you complete
Yeah,
this matrix. At some point, you see there's something wrong. You need to
Sure. But
go
so
to
but this is now this becomes because if we're defining theory through the S matrix, and then theory automatically makes selection of the vacuum. It tells us that only vacuum in which you can define S matrix are admissible.
So yeah, that's the question.
That
So
will be
what do you do
maybe
with cosmology and what we see in our
But
universe?
cosmology is not a vacuum. I
Okay,
mean,
fine.
so
Fine, so
cosmology
just
is
the
not a
vacuum.
vacuum.
Okay.
So that's why I'm saying this is we have to separate between the formulating the theory. So for formulating theory, I can give you in and out states and then S matrix, and you have a theory. Now you can go in that theory and do computations as you like, in particular cosmological computations. But what S matrix tells you, and that's an extremely powerful constraint, tells you that you cannot have vacua, which is, for example, this would include eternal de Sitter, because eternal de Sitter is a vacuum, so that's out.
But it seems like our universe is headed that way, at least locally.
How we do from where you are concluding that?
Over the measurements of the acceleration of the universe and the fact that they don't see any at least strong running of the equation of state, of the dark energy equation of state.
But I mean, the dark energy, so you have a proof that dark energy is a cosmological constant?
No, absolutely not.
Then
We never will.
Okay, but then let's stop talking about that we are in the de Sitter vacuum.
Well, I thought I
You know
would.
if you are in the de Sitter vacuum.
I thought I was careful. I said it seems to be evolving towards.
Seems, yes. But
And by the way, it has been doing that for basically half the lifetime of the
right.
universe.
And then now S matrix is telling you that that's not the case. and what you thought you were evolving towards cosmological cause, and you are not.
Well, at the risk of incurring your wrath, let me suggest that
So
it's just barely possible that there might not be a vacuum and that the S matrix version about the existence of a non-existence of a de Sitter vacuum might not be the decisive word.
No, sure, I agree. Look, what I'm trying to say is the following. When we're asking a question, when we're asking questions, we're always asking questions within the framework. And we're also making predictions within the framework. Beyond, I don't know how to make predictions beyond the framework. Now the question is, you have a concrete framework. In this particular case, let's say string theory. Now, if this framework is telling you that you cannot be heading towards cosmological constant, that's a prediction of that framework. Of course, I'm open-minded. You may say this framework may be completely wrong, and you may come up with something else, and in that something else, that's a different story. But it is a power of the framework to make predictions. That's the power of science, to make predictions. That's all I'm saying.
Okay, well, I'm definitely not against making predictions. I think we should, when the predictions don't pan out, at least the way that we made them initially, we should rethink the
Of course.
validity of the theory that is used to base them. And well, anyway.
I fully agree with that.
Okay, good.
I would stay on this full agreement, and then
No, so I mean, I'm a bit confused. I'm not sure you will agree. So because
we're going in everything.
no, because for me it's difficult to understand. So for instance, if you say that the formulation of your theory is through S matrix, so
Yeah.
basically your framework that you're used to define something is S matrix.
Yeah,
For instance, string theory, which is
let's say,
S matrix.
for example.
Let's forget about string theory. Let's just speak of S matrix.
Yes.
So you have a framework. In this framework, you have tools to do computations. And if you tell me I define everything, I formulate everything through S matrix, it looks to me that the only tool that you have is S matrix.
No, not everything. You are formulating theories as S matrix. That's not, then in that, I mean, look, in string theory, the low energy limit of, despite the fact that we define string theory as an S matrix theory, the low energy limit in string theory gives you Einstein gravity. Okay, with some developments and stuff. Of course, in that theory, you can solve equations and find solutions. And string theory incorporates all the solutions of Einstein gravity because it has in low energy limit Einstein gravity. So in string theory, you have Keplerian orbits, you have.
Yeah, sure.
Right.
In that case, you will recover GR with a massless spin 2 with some type of S matrix, which incorporates the vectices and the propagator.
Exactly. S matrix.
How do you get the
still-
power spectra as S matrix elements?
This is what I was trying to say, that you don't need to get the formulation of the theory in terms of S matrix. It tells you that your degree of freedom is graviton, it has asymptotic states, it has vertex operators. Okay, in string theory you have more than graviton, but it doesn't matter. So you have vertex operators, and you can vertex by vertex, for example, reconstruct Einstein gravity, Einstein Lagrangian, then hard derivatives and so on. Now, since you have Einstein Lagrangian, you can do everything that you can do with Einstein Lagrangian. Of course, there are some constraints on sources and stuff like that. So that's the way it works. So I mean, you don't need to solve a scattering problem to reproduce cosmology. That would be a waste of time and energy, and you probably will never do it.
Just a small clarification. So what you're saying absolutely right, but once you get to the point that you found your S matrix, you say, okay, now I reconstruct effective action, which gives me this S matrix in that vacuum. But that effective action, that's an extra assumption because it also knows about other vacuums.
Absolutely, yes.
So that's an extra
absolutely.
assumption.
No, that's a very good. No, thanks for that. So
The
indeed,
extra
this-
assumption is called local field theory.
It's extra
Yeah,
assumption
no,
that there
this
is a bigger framework.
absolutely. This is absolutely correct remark. So the vacuum of the theory doesn't have to be unit.
But see, then I would say that it's the local field theory that's the
No.
fundamental thing.
No. You can have it, or you
It's
can
a
also
source of information. How do you know this local field theory? You reconstruct it in a given vacuum from.
right. You can have theories. You can have effective field theory or string theory. We know has this property. You can have theories which have multiple vacua, and in each of those vacua, S matrix must be definable. If your theory is defined through the S matrix. Of course, it's a very good question. Then whether S matrix is defined in one vacuum carries information about the other one, and this and that. These are, of course, all open questions, extremely interesting. I mean, nobody denies that these are deep and fundamental questions. Obviously, I mean,
In a string context, in what happens, that you have flat space asymmetric, you construct effective action, and you discover that extreme of this effective action actually describe other conformal two-dimensional sigma ones,
Absolutely, yeah.
which are other vacuum
Yes,
strings.
exactly.
So
Absolutely.
it's all kind of consistent frame.
Absolutely, yeah.
So just to understand if I understood. So the logic is the following. You say I use S matrix to formulate, for instance, a theory for a massless spin-2 particle. So it means that you will have some at some energy scale, some vertices, some propagator. Let's suppose we are working at some low energy where we expect GR to be recovered. So by looking at the S matrix, you try to construct some effective Lagrangian that could recover these vertices and propagator, which for instance is GR Lagrangian. And then you say, given that this effective Lagrangian that I constructed in this energy regime, I can use this Lagrangian with fields, even to compute something which is not a matrix element, but cosmological operators.
Absolutely.
And this logic is fine.
I hope so.
I don't think it's necessarily fine. Let's take some of the more extreme things, maybe not necessarily things that people here believe, but things that I've definitely heard all the time. For example, the people who believe in higher derivative gravity, in particular the c² term, will argue endlessly that the massive spin-2 ghost is not a real physical state, so it doesn't screw up unitarity because it's not, it would decay. And of course, it would decay. It's not going to be present in the asymptotic space of states. I think they're confused about the problem of the closeness of theory, but they would argue that. I'm not sure you would recover the field theory from which everything came there. And to put it in a completely physical context, let's take the currently best theory of cosmological inflation, the one that was proposed by the late Alexei Starobinsky, R plus R squared inflation. There, the R squared, the Eddington term, is okay. It doesn't have a negative kinetic term, at least as long as the coefficient in front of it is positive. And yet, it does have a massive scalar associated with it, and that massive scalar would presumably decay into gravitons, so it's not present in the asymptotic state. How are you going to recover that? You've got a theory of massless spin-2 particles, and the massive scalar, by the way, plays a hugely important role. It's the thing that serves as the inflaton during, like I say, what the data is telling us is the best motivated model of primordial inflation. It seems to me like there's a lot of things that might go wrong in this reconstruction.
I'm not so very interested, but I'm not sure. Let me see if I understand the question, because you started with the theory with the ghost, which is beyond my.
No.
I just gave that as an example.
Then
earlier.
Of the kind of things that people who insist on S matrix formulations typically use as dodges to avoid what are just manifestly, glaringly obvious problems in their theory. They say, these ghost particles aren't present in the theory because they're massive and they decay. Okay, let's apply it to a theory that doesn't have ghost particles, that is a good theory, one that we believe is true, namely R plus R Starobinsky inflation. Same thing.
Let's say
the massive scalar is going to decay.
Very good.
So it's not present in the asymptotic space of states. Would we actually recover that theory?
So, asymmetric theory doesn't tell you. I think that for that you don't even need strict theory. In standard model, there are plenty of particles which are unstable. In the asymmetric theory, nobody says that all the particles have to be stable and have to be asymptotic states.
Whoa. Excuse me, Gia, people do say that all the time. I know because I get called to referee these papers of these people who believe in the c² term. They believe passionately in the c². And one standard dodge that they use to say, no, it's not really there because those massive spin-2.
No, sure, but this is not good argument to argue with me, because I can argue from what I'm saying, not some other papers that write something.
But see, you said people wouldn't say that. People do say it.
Which people? I don't understand. The question
I
was
don't
very
want to put
concrete,
words
right?
into somebody's
No, wait a minute,
mouth, but let me do it.
You are deviating now.
So,
No, wait a minute, you are
so
deviating,
our
you are deviating.
asymptotic safety colleague, who is not here, was saying again and again and again that they believe that they're going to get a weakly coupled asymptotically safe theory. And it seems to me to be just obvious that it's going to have a c-squared term in it. It's when they reconstruct the local theory behind it, it's going to have a c-squared term. And let's see, there are some asymptotic safety people here.
Yeah,
You,
but,
for
but you don't
example.
have only the c-square, you have.
No, I think we departed from the question. Question was very concrete. Question was,
Could we reconstruct the action of general relativity by just knowing that it's an interacting massless spin too? And I think no.
but obviously you have other particles in the theory. Massive spin 2 was an
As
example.
resonances,
No, for example, electron photons are there, those are stable.
those are physical things, but I gave an example of one that would just be a resonance, the Star-Binsky
Yes.
scalar.
So if the question
AKA
is,
the
yeah,
influence.
if the question is whether S matrix can account for resonances, the answer is yes. S matrix can account for resonances.
Well,
It could be that in principle, I mean, this matrix approach, at least one you are taking, doesn't need to reproduce R plus R squared. So
No,
in that case, you would discriminate between.
but we better reproduce it because that's the
I know,
leading
I agree with
theory.
you that
I'm
I
putting in
also
place.
am interested in Star-Binsky inflation.
Yeah,
But
this is a different. So let's separate two issues. So one was about resonances. Okay, S matrix, of course, it reproduces resonances. All these computations we do for LHC and stuff, most of the stuff are resonances. Now there is another question, which is also an interesting question. There is your favorite, or maybe many other people like it, a model of inflation, particular model of inflation by Star-Binsky. And now the question is whether this particular model can be recovered in string theory.
Yeah.
They are favored.
Whoa. It doesn't really, again, forgive me, it doesn't really interest me so much whether it can be recovered in string theory. The question is whether you can, by knowing that you're dealing with a interacting spin 2, massless spin 2 theory, whether or not you can recover the R plus R squared theory of gravity.
You will recover it as a theory of R plus phi plus potential.
Right.
What's wrong with that?
What's wrong with that?
Well, would you? I mean, they would say that the massive particle is not part of the spectrum. How are you going to see it?
I don't understand what we're talking about. That's certainly not the framework I'm talking about. Maybe so. I mean, for me, it's very hard to answer questions beyond my framework. So in my framework, there are plenty of massive particles. Some of those could be even stable. Some of those would be unstable. If the question is there any conflict with an S matrix? The answer is no. There's no conflict with the S matrix.
I mean, depends on the full theory that you have. I mean, some theories at low energies then only have like the graviton. Some other theories with other ultraviolet completion, for instance, quadratic gravity, it would have the graviton, it would have the scalaron, it would have the spin 2 ghost.
Yeah.
In asymptotic safety, you have to check the spectrum, but the point is, it is not obvious that if you have like only R square and C square, or if they are in the low energy expansion of your theory, then automatically you have the spin 0.
The C-square ghost is what I want.
Yeah, but if you have the C square, okay, unless you are in the framework of perturbative quantum gravity, where you only have those terms and therefore you necessarily have those extra states. In general, you would have a whole tower of higher derivative operators, and if you then compute the fully dressed propagator, depends on what your theory is, you can have these states or not.
Well, I'm talking about the final step in the program, which is to take the cutoff to infinity and recover the local theory that this represents a quantization of. And it seems to me just obvious that the result they're going to get is that it represents a quantization of Stelli's theory.
No.
I know you don't agree.
I don't want to feel.
I know you don't agree.
I really
Let's agree just to disagree about it. You haven't done it yet, so we don't know one way or the other. But it seems to me, this is my opinion, maybe I'm wrong, but my opinion is that it's likely to recover Stelli's theory, and that's the reason why it is that the theory is giving finite results that make sense when you extrapolate them down to the infrared, and then I foresee that what's going to happen is that there will be very long and involved arguments about how the C-squared ghost isn't really there, and it doesn't prevent the theory from making sense.
So I think the topic of the discussion is different, but
We're going towards prediction that is not.
but briefly, I mean, our UV completion is not stellar gravity. Otherwise, we would have a perturbative normalizability.
It's a different fixed point.
It
You
is a
can
different
see
fixed point.
the stellar fixed point, but it's a different fixed point than we see. We see both of them.
I mean,
so
we
it
would have
cannot be
more
the same UV completion.
If you compute the Bay reaction, you see that you have extra terms of your stellar. In the UV, in the limit, your lambda that goes to infinity.
I don't know, maybe it's an S matrix question.
No,
Yeah.
I think
Well,
we-
that is
somewhere
true.
else.
If you're at dinner, because maybe you can talk about the dinner, but it's better than here.
If I can just maybe close the topic about S matrix and.
No, we don't want to close the topic.
No, sorry, I think about what the. No, yeah. I want to close the point that he raised. So, okay, I think the logic is more clear now. And in your case, if you said you want to describe only a massless spin 2, as you said, if you increase the energy scale that you're interested in, you would also maybe generate extra vertices for higher derivative and so on.
Absolutely.
In that case, you may also have a square and so on, but in that case, it would be only correction. It will not have large coefficient in front of it. That's why you will not have an extra degree of freedom.
Well, the question is whether you would reconstruct Stravinsky's theory, and in particular, I take the space of states as being in one-to-one correspondence with the degrees of theory, the degrees of freedom of the theory. And if we really do need that extra higher derivative degree of freedom that's present in that theory to have initial value data associated with it, it seems to me that the statement that it's not really there, it's not present in the asymptotic state, space of states, is saying that it doesn't have those degrees of freedom.
But that's, again, let's.
I think that's a misunderstanding of what S matrix formulation means, because as I said.
Okay, so resonances
In the
do have degrees of freedom, right? They have initial value data associated
If
with
the
them. that
resonances are not
correspond to-
terribly broad, they are counted as degrees of freedom, like Z boson, for example. In the standard model, we're counting like a degree of freedom, although it's unstable. You will never see it in the asymptotic, as an asymptotic state. It will decay, right? But we do computations, and S matrix accounts for those. But this is somehow a technical question, which the answer is yes.
Oh, no, it's not a technical question,
but
because you're
you-
claiming we can reconstruct from the S matrix, we can reconstruct the local field theory. And this is at the heart of being able to reconstruct the field theory. As I understand, and I deal with this endlessly because I get asked to referee papers by people who believe in higher derivative gravity, who believe that the Weil term is okay. They are arguing that that's just not present in the theory, and there's no initial value data associated with it. It's just not there. You're saying, no, they're not formulating S matrix theory right. It really is present.
I cannot
It really
argue
does
about-
have-
The only thing we can do
I
is
cannot
note
argue
the
about-
complaint again.
I cannot argue about, I just understand this from your description that you are describing now. If someone has a theory.
I will refer the next paper I get, next referee report that I get, referee request I get on this issue to you.
But I think I understood. So you are saying if someone makes a claim that particle that is unstable, but by the way, if you have a ghost in the theory, that's outside of my framework. I'm not even interested to discuss that theory. Okay. So let's restrict the discussion to the healthy theories which have positive norm, no negative norm states, and things like that. But if beyond that someone makes a claim that ghost is okay, I don't know. This is a question that I would not enter now in this discussion.
But see, the reason that they make the claim that the ghost is okay is because they say that's an unstable particle. It isn't present in the asymptotic space of states. It's just not there. You shouldn't include it in the sum over states, and it doesn't correspond to.
I don't even know what unstable ghost means, but because I don't know. Usually,
it would be nice if they could have, if there was a proof of that. That would be interesting.
They say
That
it
would be
as though
non-perturbative.
it's just, they say it
That would
as
be very
though it's just
non-perturbative.
obvious.
We were going towards
anyway,
psychology.
but let's come back to the thing, right? So they are very concrete questions. Let me only consider theories which are ghost free, because ghost free constraints is one of the fundamental constraints of the framework that we're working. So in that theory, you can have unstable particles. And there is no issue of incorporating unstable particles in the theory that is defined through this matrix.
And they will have initial value data associated with them, right? Independent degrees of freedom that somehow don't get put into the sum over states.
Let me give you an example of the standard model, right? Forget about quantum gravity, standard model. In standard model, you have Z, W bosons. They are all unstable. But you do find, for example, spirals as solutions of classical equations of motion, and you trust them. Because everything in physics is about regime of validity and of time scale. If I'm interested in phenomena at the time scale is much shorter than the lifetime of a Z boson, I can treat Z boson as a stable particle. I can forget that it's unstable and look for classical solutions, some spirals, instantons, these kind of things, and then incorporate them.
Yeah, but
so
now,
it's all about time scale.
Now you're talking about treating it as if it was
because that's legitimate.
Well, I'm totally happy treating every degree of freedom as if it's fundamental, but I'm telling you, there's a huge body of people who allege to be quantum gravity experts who do not accept that. They will only insist.
But this question has nothing to do with quantum gravity. You can ask it in standard model.
Does have okay. So it does have a lot to do with quantum gravity in the following sense. And that is, can you reconstruct, by knowing the S matrix, can you reconstruct the local action from which this came, or the local Lagrangian from which that S matrix came?
Yes, the answer is again, so since the problems are about validity regimes, what does it mean when I'm reconstructing, when I'm using effective Lagrangian, right? Effective Lagrangian, the term tells us that it's an effective description of something. Now, this effective description has a validity range. Validity range can be limited by time scale, if you are interested in some cosmological problem, or it can be related with energy scale and so on. So the answer is that in this framework, so far, you can, within the validity of those effective descriptions, this procedure works. That you have vertex operators, you have acyclic states, you construct vertex operators. And
put it in concrete terms, would we reconstruct Starobinsky inflation? Could we reconstruct that from the S matrix?
I don't see any fundamental difference.
We have resonances at 10 to the 16th GeV are actually probably going to be more than that.
I didn't try that. That's maybe an interesting question. I did try that because
I think some people, including even some people here in the room, would say they're super Planckian, they'll form black holes, they're not even present.
No, those are separate. There are certain complaints against Starobinsky type inflation. Because those complaints are, a priori have nothing to do with the S matrix. These are different nature. For example, in string theory, it's very suspicious when you have variation of a field over a range much larger than the Planck scale, or even comparable to the Planck scale, few times. So there are some arguments against that. There are arguments about strong coupling, this and that. Those are not directly related with the S matrix. So let me put them aside. But if you're asking a question if Starobinsky inflation can be embedded in an S matrix theory, I mean, I didn't try it, but I don't see any problem.
Okay, I'll give you one problem. The mass of the particle would be bigger than the Planck scale. I think there are people, including people in this room, who would argue that that's just not, that you can't do that those kinds of things would form black holes.
Yeah, I think that's correct.
Elementary. Those people. And so how, from the S matrix, would I recover that theory?
So again,
why is it bigger than Planck mass?
The mass of the inflaton.
Yeah, 10 to 13 GeV would be Starobinsky.
16.
Not 13 GeV. It's like
that's the Hubble parameter associated.
So the mass of the scalar is 10 to the 13 GeV, which is slightly smaller than H during inflation. So it's 500.
That's not my understanding. My understanding is that it's bigger.
No, it's smaller. The mass of the scalar is smaller. But then you will change it.
In any case, if one second more,
there's a suggestion is to tunnel to a different black hole.
Yeah, I think that actually that is just depending on your fundamental theory. It can be string theory, it can be asymptotic state, it can be anything. It will tell you if it is predictive what are the asymptotic states of your theory, and then it can be that it has the scalaron of Starobinsky inflation, it is possible that it doesn't, and it has a different mechanism to produce inflation.
Well, so you're starting with an action, and I'm happy doing that. The other people are saying, no, 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 no. We can take the S matrix as the definition, and indeed the S matrix even on flat space, use it to reconstruct the local Lagrangian, and that then everything that I would want to do in local physics or in cosmology, I can do using that local Lagrangian, and I have some doubts about that.
I mean, you don't need to necessarily use an action. I mean, in different approaches, you may use the different tools like just amplitudes, or using an effective action that doesn't necessarily, it doesn't need to be local. Also because you have
in fact, I'm sorry to interject something here. I remember from the old days of S matrix theory, this used to be known as the inverse scattering theorem, or the inverse scattering theory, and there was an issue about whether or not the S matrix really did completely define the local quantum field theory, and I think they never resolved that. I think that's not a theorem, that if you have the S matrix, you can reconstruct a local quantum field theory. I think they had something they called CDD poles or something like that that would preclude getting an answer for that. So I think that's just not a fact and evidence that you can.
But there are also S matrix approaches that go beyond quantum field theory, and you don't need to have a Lagrangian to have an amplitude. So you don't really need to. I mean, of course, at low energies, you want to ask the question, how do I map my S matrix elements into a Lagrangian at low energies, but at high energies, you don't need to. And in particular,
I do cosmology, which is sort of the ultimate low energy experiment, and I don't want to be put within the straitjacket of having to have an S matrix. I'm happy not having an S matrix.
But that was actually something that everyone agreed here on, right? There could be frameworks where you don't need the S matrix, and there are other ways to compute your observables that are definitely more useful. And that probably everyone also agreed that once you go to cosmological problems, then there's many questions that come up, and then maybe S matrix understanding could be one of them. So I don't know.
Philip has hand raised
Yeah.
sometime already. Let me unmute you. Philip, go ahead. You can unmute yourself.
Yes.
So 1 second, we cannot hear you.
Can you hear me? Hear me now? Hello. Okay, good. Hello, everyone. Good afternoon. I have a couple of questions. One is about reconstructing theory starting from the S matrix. Has anybody ever shown that if you only have all possible hadron S matrix elements, that you could come back to QCD? I don't think anyone's shown that. So if that hasn't been done for QCD, I'm not sure how it could be done for gravity. That's the comment. Now, the other thing is, as regards S matrix, my understanding of the unitarity of the S matrix is simply the statement that the set of states in the Hilbert space is complete. So let's not consider graviton-graviton scattering, but let's consider proton-proton scattering. Now, we know that S matrix theory works very well at current energies, but that has an implicit implication for much higher energies, because the analyticity of the S matrix allows you to write a contour integral, and you have to be able to suppress the circle at infinity. And that involves very, very high energies. So there's some implicit high energy information in low energy S matrix scattering. Now, even if you discount that, you still have to ask the following. You do proton-proton scattering, elastic scattering, and you keep on increasing the energy, and then let's say you reach Planck energy. What happens? Does the set of in and out states suddenly stop being complete? I mean, that's basically the question that you have to answer. And those are my comments.
About hadrons, at least in 2 dimensions, in integrable models. You have solitons, you have spectrum elementary excitation of solitons. So you can actually see in this solitonous matrix more or less everything. You don't need to look at solid matrix of elementary states. So if you knew the complete spectrum of hadrons, well, these, of course, solitons are kind of stable. That's, of course, the integral model. So it may not be the right framework here. But my guess would be that if we knew everything about hadrons, we could probably figure out what are the elemental states behind that. It's major. But we need a lot of information.
No, I think so. I agree. I mean,
But then you're answering Philip's question, no, nobody really has shown it yet.
No.
well, because it's difficult.
But
I mean,
it's,
nobody tried even.
it should be a statement about confining theory.
Yes.
I mean,
which is non-trivial. Yeah.
you can certainly reconstruct a chiral Lagrangian. So if you have, okay, let's take idealized situation where quarks are massless photon. So you can reconstruct chiral Lagrangian, it's Lagrangian of pion, for example. Then, so in principle, yeah, I agree. In principle, if you would have infinite precision, yes, the answer would be yes, you could reconstruct the full theory. Okay, that's a technicality. Again, we are hitting this issue which I was trying to disentangle. The formulation of the theory in principle from the computational power. The fact that you are formulating theory in terms of S metrics doesn't mean that you have to really know and be able to compute all the elements of the S matrix. We don't know that in any theory. It's just, it should be definable. So, yeah. So that will be my answer.
Other comments on this? Other questions?
I have a comment. I mean, in string theory with the S matrix, you can compute the multi-loop amplitude. And by solving together three diagrams, and you get so you can go a bit of shell in such a way that you compute multi-loop. And then when you have computed multi-loop,
well, excuse me, why do you say going off shell? Isn't that using Feynman's tree theorem, which is explicitly on shell representation of them?
No, I mean, when you compute the loop, I mean, you need to construct an object which is BRST invariant. And then you can put a propagator which is BRST invariant. And then you can close together and get a multi-loop.
Absolutely, but I think the constructions of how to get higher loop things explicitly use on-shell stuff. I think there's a way of writing, although we usually don't do it, there's a way of writing every loop amplitude as explicitly on-shell things. And I think that's what's done.
Yes.
Okay.
But also, when you have computed multi-loop, you can take the alpha prime limit and you can reconstruct the Feynman diagram of various. For instance, you can compute the one loop beta function in Yang-Mills theory. You can compute it has been computed up to 2 loop for phi cube, for instance.
Okay, so let me pose you this question. From string theory, reconstruct the fundamental theory from which string theory came. Tell me what the dynamical variable is and what equations it obeys. As far as I know, nobody's done that. There are answers to it. It's just that people don't like the answers. One obvious answer is string field theory, but people don't like the fact that it would be non-local in any representation, and it would presumably suffer from Ostrogredsky instabilities. And so that's rejected as an answer, and it's asserted that this is still an unknown problem. And
people are working actively on string field theory, and there's many interesting progresses coming out. It's just the field becomes more and more technical, but questions are being addressed.
But one question that isn't addressed is how to prevent the universe from blowing up just like that, right? The string field vertices, the reason that See, being in extra dimensions doesn't make the theory more finite. Being in extra dimensions makes it less finite. Having the infinite tower of states doesn't help either. The thing that makes string theory vertices finite, or makes string theory amplitudes finite in the context of quantum field theory, is that the vertices have factors of e to the minus p squared on them, which converge like crazy in Euclidean momentum space. And then the issue associated with that is, okay, look, is that allowed? I would say no, but if it is allowed, why not just throw away all the baggage of string theory, the supersymmetry, the large extra dimensions, or the extra dimensions and the infinite tower of states, and just do that on Yang-Mills theory or do it in gravity? And I think the answer is that you can, and it will suffer from exactly the same problem as string theory does, namely that non-perturbatively, those theories are higher derivative theories, and they're going to be unstable, virulently unstable. And I don't think anybody's addressed that issue. I think it's just people are refusing to face that issue.
So I think that first of all, in many approaches to quantum gravity, you will have to give up locality. In many approaches to quantum gravity, you will have to give up locality in the ultraviolet. And now, if you go into the framework, I mean,
well, the question is which kind of locality. So there's a particularly bad sort of non-locality, because non-locality by entire functions, like e to the minus p squared.
Mm-hmm.
First, that doesn't even work very well in Minkowski's signature, which is what describes the real world. You couldn't, for example, explain to a numerical relativist how it is to numerically simulate something like that, because it requires an infinite amount of knowledge in the future in order to do it. It only works in this sense of restricting yourself to calculating loop amplitudes on Euclidean momentum space. And that's the kind of non-locality that I think is really deadly. And that's the kind that exists in string theory, precisely because they don't want to introduce new cuts and folds into the loop amplitudes, except the ones that are already associated with stuff that was present in the tree spectrum.
There was a question there.
I think so.
Sorry, there was a question. Thank you. Sorry.
Yeah, but unrelated to that. So yeah. So I mean, my question is, if you take that idea seriously, that we only look at vacua that are compatible with the S matrix description, then what happens in that case to the cosmological constant? I mean, I think what was said is, okay, we have to set it to 0. Everything else would be incompatible with it, and dark energy is something evolving, fine. But then what happens to the? I mean, do we have a low energy understanding of the smallness of the cosmological constant in that case? Are we? I mean, that would be my question. Or are we kind of giving up on that goal of finding that? Yeah. I mean, how does that question change?
Well, I'll address that. I don't give up on it. I think we should look for a low energy understanding of that. The one that I've been working on for years that I expect nobody in this room agrees with is that that inflation, primordial inflation, creates a sort of quantum gravitational friction that gradually slows the expansion of the universe. We don't observe the cosmological constant directly. What we measure is the expansion of the universe. And I think that the cosmological constant, the bare cosmological constant, is not small, that it's big. But that's the thing that started primordial inflation, and that it then generated this vast ensemble of cosmological scale gravitons that gradually pushed the universe gently up to the point where it was almost within its own Schwarzschild radius. And then that brought the expansion to a close. And the reason we see almost zero expansion is because we're sitting very, very close to that limit right now. But whether I'm right or not, I think we should look for a explanation of why it is that the measured expansion rate of the universe is so much smaller than the natural scales of physics.
Yes, I mean, this is a absolutely correct question, and as I tried to say, so yes, that is a prediction of S-matrix theory, S-matrix gravity. So the S-matrix gravity unambiguously predicts that in our universe, the energy budget of the universe cannot come from cosmological constant. I think that's great news because theory makes a prediction, which means that, as you said, dark energy should be some kind of degree of freedom, which evolves in time. Now, then, of course, this opens many interesting questions. I mean, by the way, myself, I was never a fan of this type of thing, like quintessence, or I always, before I realized this thing about S metrics and convinced myself, I thought that cosmological constant was the simplest account for dark energy. But so but I mean, then this opens this question, which is a very interesting question. I mean, there must be some physics beyond the standard model and the degree of freedom that evolves in time. And then all these questions that you said, I mean, you know, why is this degree of freedom so light? I mean, people have constructed many models of quintessence. So quintessence is technically natural. So you don't need to find, because it's protected by shift symmetry. So if you have a field that is minimally coupled to gravity, the mass of that field could be arbitrarily small. So from that point of view, it's not an issue. But yeah, it's a very interesting new set of questions. So
Well,
I
what
fully agree.
happened to the bare parameter lambda in
It's zero in S matrix.
It's exactly zero.
Yeah, by consistency. It's like anomaly constellation, right? Or maybe, by the way, if you are suggesting some other mechanism how lambda can change in time, that's the same. To me, it would be the same. If someone tells me that lambda is changing in time, for me, that's the degree of freedom. That means that you have a field that changes it. So it's effectively should be equivalent to a field that just goes down.
More comments? Other questions? We still have some time.
I'm just formulating my question because you say that the cosmological constant must be zero.
But in this framework, again, I mean, within
S matrix.
within S matrix.
But also string theory can be formulated as in terms of S matrix. And if I remember correctly, one of the conditions that come from the I mean, there is a technically cosmological constant that can come from string theory. It's just that it is it can also be negative, right?
Yeah, actually, exactly. That's a good point. So it can only be negative.
Negative or zero.
Yeah, zero, of course.
I mean,
zero.
I remember that there is this condition that comes from the binary anomaly cancellation. It is an expansion in the curvature, and the first term, this should be the cosmological constant is something like d minus the critical dimension over something, and that's what defines the cosmological constant. So it can be.
Yeah, so string theory can consistently have ADS vacua. There's no problem. It can have isolated ADS vacua. And then Minkowski vacua, which are degenerate. You can have as many as you like, this Minkowski vacua, but they have to be degenerate. But by the way, this is sort of, I can tell you the personal story, because we were trying very hard, like 25 years ago or something. It started with Henry Tai and myself. We were asking precisely this question: can one get the sitter in string theory? And it was around that time, slightly before, when Joe Polchinski introduced his D-branes. And previously, because in order to get the sitter, you need something with negative pressure. You need a source, a momentum source with a negative pressure. And then we came up with this idea that maybe we can use D-branes for uplifting and to the sitter. And it always failed. We could never stabilize it. I don't know. Personally, I invested, I don't know how many, probably 5 years of trying to come up with a stable de Sitter or metastable, something like that. It never worked. And of course, in each case, it's a very good reason, theory, why it doesn't work. But so, and then I realized that because theory tells us that this cannot exist, because otherwise it will be a vacuum, and theory cannot have a de Sitter vacuum because it's not matrix theory. So right, yeah. So indeed, in string theory, I mean,
But metastable de Sitter would be fine.
No, because that also contradicts with the S matrix. So if the metastable de Sitter, you see, the problem is that in metastable de Sitter, you can tunnel, but the tunneling rate is so suppressed that most of the universe continues to inflate. Correspondingly, again, globally defined time, global time cannot be defined. So it doesn't matter whether the de Sitter is unless the barrier is very shallow, so that you can really finish inflation in the entire universe. So yeah, so that's a very powerful constraint. So you cannot have metastable, stable. So it has to be Minkowski. You can have temporary. You can have inflation. Inflation is not a problem.
Maybe just a very naive, at very naive level. So indeed, there is some connection between anomaly cancellation and cosmological constant zero, which you mentioned. At the tree level in string theory, the cosmological constant is d minus 10. So it's if you are canceling conformal anomalies, you are sitting in the vacuum when no other fields are excited. Then it's equal 10, and you don't have cosmological constant. That's where this matrix near flat space appears. Of course, you can have other vacuum, and like in the de Sitter balance by some fluxes, and then you still it's d equal 10, but you have curved space, curved metric, and some background. If you try to do this with de Sitter, it's never consistent with supersymmetry, it's never stable. So there will be some problems like whatever, tachyons or
so there's always
so your theory wants to go somewhere else. That's basically it.
So are these KKLT constructions?
But that's kind of effective. It has some peak.
They're unstable.
Yeah, they could be stable in some region of evolution, but they will never be globally defined. And
yeah, I mean, okay.
Yeah, you can comment.
None of those people are here, so yeah. I don't want to criticize the.
Okay, their construction. There's a long debate whether
I don't think this is stable. So I don't think that.
But the point, I think the point is that if we knew, for example, you can say, what about maybe there are some other string theories. If we could define bosonic string theory without tachyon, always there is an issue of instability. So that's what we need to watch for. So,
I mean, there are non-supersymmetric theory, which seems to be consistent. Also, all these theories,
but not with de Sitter vacuum. Yeah, they are non-super. Yeah, I agree. Yes, there are examples, but then you don't need to have tachyon. You don't want to have tachyon.
I mean, is a theorem or is a
what?
It's a factor that you observe.
I think it should be close to a theorem that if you want to have no tachyons, you should have supersymmetric vacuum, and de Sitter will never be that. So it will be unstable. So once you...
So we do seem to see the universe accelerating and heading towards a locally de Sitter state over 6,000 megaparsecs.
There's no problem in Einstein theory. It's not just string theory. It's not UV complete theory, and of course it could be.
So you're saying that somewhere else in the universe that we can't see, it has to not be doing that?
Yeah, it just this framework doesn't allow it. It doesn't mean that it describes the universe. It could be something else.
Yeah. So I guess I know it will make you angry, but I'm open to the possibility. Perhaps
I'm tired of saying the same things.
Not correct, or that supersymmetry is perhaps not correct, and that there really isn't that constraint on the.
A lot of things which we learned is through guidance through supersymmetry, and that's true. But unless we have something better than that.
Can I follow up just this one thing? I mean, I'm very happy to accept that there is no de Sitter vacuum in string theory and so on. And then, okay, if you say the cosmological constant is exactly vanishing, I still wonder. I mean, and I'm also happy to accept there's dark energy and we can write down a quintessence model and it's radiatively stable. That's fine. But we can still calculate quantum corrections to the CC. So we are going to see masses, particles with different masses are going to give different contributions, fermions, different sign and bosons, and so on. And the only way we can make that work is to say, okay, all these contributions cancel against the bare cosmological constant. It's fine. But then we are willing to accept that, right? On the basis of S matrix consistency, right? I mean, then we say this cancellation must happen because otherwise S matrix is not consistent.
Mm-hmm. Yeah, correct. It's like anomaly cancellation. I mean, there is these are in theory. I mean, cosmological constant, as you said. This is an example of UV sensitive quantity.
Yeah.
So it's sensitive to it's directly sensitive to the cutoff of the theory. And such quantities correspondingly cannot be computed by default within effective field theory because they are cutoff sensitive.
Yeah.
So we can only estimate, and that's why for a long time we thought that there is a cosmological constant problem because the corrections, naive corrections look huge, and then different contributions should cancel each other.
We don't still think there's a cosmological constant problem?
Well, not in string, because string theory tells you that cosmological, no, there is this dark energy issue. That's a separate story. But I'm saying the constant has to be zero by consistency in this framework.
So conversely, if the universe does have a non-zero cosmological constant, a positive cosmological constant, then string theory is wrong, right?
If you can really prove that it's a real constant, yes, but that's very difficult.
We're safe so far.
This is a really naive question that I have. Is just something that I don't wanted to.
No, it's fine. Yeah.
This is something that I still don't understand. I mean, the states that define the S matrix, the theory, or whatever. I mean, saying that there cannot be a de Sitter asymptotic state. Does it really mean that I cannot have a cosmological constant in the effective action, or does it mean that its solution cannot be de Sitter? Because it's a different statement, right?
Well, I mean, yeah, you should. I mean, you cannot have so in the let me answer like this. So in the effective theory, because this is the power of the S matrix, that it's directly sensitive to the vacuum of the theory. Okay, so therefore S matrix is directly sensitive to the deep infrared properties of the theory, right? So now if you go into deep infrared effective field theory, and then in effective field theory you solve whatever equations you get, and you come up with, you tell me, this is my space-time metric. This is what is important. Because how you get the space-time metric is a separate story. Now, naively, I would say, since Einstein theory is valid, then cosmological constant, if cosmological constant enters as a source, then you will get the Sitter. But maybe you have some modification or something.
No, but in general, I mean, if you have like a random would-be completion of gravity, you would have corrections to the.
Yeah, all corrections summed up, all corrections fully summed.
Exactly.
Should give you the asymptotic metric to Minkowski, asymptotically flat. So if it gives, so it should not give you the Sitter.
I mean, if you have, in principle, even if you have something like a cosmological constant at this point, you go in the Lagrangian, okay?
But that doesn't generate the metric, you mean?
No, doesn't necessarily generate the Sitter. I mean, you can have something like a cosmological constant Einstein-Hilbert plus the tower of higher derivative terms that when you expect in field theory, you derive the field equation. It is not obvious that you get Ricci-flat solutions.
Yeah, okay. So you probably mentioned this idea of degravitation of cosmological constant. So yeah, so actually we had this, we investigated this. This type of proposal collaborative.
So I mean, even if you have a cosmological constant in the atom, doesn't imply that we have.
Right. Yeah. If you have this sort of some kind of infrared modification of gravity, maybe you can have a situation when you have a constant. But for the S matrix, that doesn't matter. That's also power of.
Yes, I agree. Right. That was my point.
Because it doesn't matter what the S matrix for S matrix is important is space time. So the space time should be asymptotically flat. So
the vacuum of the come from the atom, not the terms in the atom.
Allow it to be asymptotic ADS.
Asymptotically ADS per se is fine. The only problem with asymptotically ADS, if you are, as you know better than me, if you're coming from some kind of a de Sitter or FW, and then you move to ADS, usually you get the crunch story, and then it's equally problematic for the S matrix. So if you somehow manage to end up in a sterile ADS, then no problem. ADS is no problem. You can have exact supersymmetric ADS. Per se ADS is not a problem. But very likely we cannot be heading towards that, because then we would end up in big crunch.
The latest is we're heading towards the Sitter.
Yeah, that's what you said. So that's why. So the Sitter or something like the Sitter. Yeah. I think the correct statement would be that we're heading into a quasi-de Sitter, semi-de Sitter state. We are in semi-de Sitter state, but by no means we know that we are in the Sitter. We don't know that.
Okay, but it's been going on for a long time, about half the lifetime of the universe. I think it's probably a good idea to keep open the possibility that that might just be what is happening.
Well, not in this framework. That's what I'm telling. In this framework, that cannot be happening. Well, the prediction of this framework is that there must be zero.
That framework is.
Until we have measurements that
Okay.
you can't feel any of them.
If I can add something, what we actually measure is not the cosmological constant, but the omega lambda, and that is like the sum of stuff. It can be cosmological constant, scalar fields, everything that
Yes, of course,
contribute
absolutely,
to
yeah.
the dynamics. And I mean, I was told by astrophysicists that it is extremely tough, if not impossible, to detect whether whether you have variations. Whether you have a constant lambda or something that varies.
Claiming to see some small variation in it right now, but it's very small and tendentious, and that would, of course.
And that would be compatible with.
But then
that would
would
invalidate an exact.
in our favor. I mean, then you are insisting that it's no, but then you should not insist that it's constant.
I'm not insisting.
Okay,
What I said is that the data seems to be pointing towards a de Sitter phase, and it's been going on a long time.
But new measurements may
That's the lifetime of the universe, and the new measurements might be pointing in the bad direction for you all, not rather than the good direction.
I mean, Richard, it's probably a matter of taste, but I think we are very young. Our Hubble, we are very young.
I don't feel young.
Our Hubble is very young, so and it's only 70% of the budget that comes from there. So I don't know why you are saying that we are in the system.
there's a
So just on the variation on this DAISY result, I just saw a paper yesterday that said this is likely a supernova. Like if you select out different supernova, it goes away completely. So you have absolutely, so then
So it's a selection
there seems to
effect,
be
right?
a selection effect going on there in this slight hint that there is any effect away from the center.
Yeah, that's a pity. But
So it's even worse. Or better.
Can I ask a question? I mean, does it mean that this non-supersymmetry theory that have a non-zero vacuum energy, the vacuum energy is always negative?
You mean non-supersymmetric theory? You mean string version?
I mean, there have been a lot of non-supersymmetric theory recently computed, Sagnotti et al. Now,
you mean
I think yes, they were never
they're
claiming.
always negative.
They should be.
They should
They
be,
never
should be.
claimed de Sitter. No.
Yeah, this should be, yeah. No, the Sitter per se, there were two stories that met because, as I said, per se, this issue of people trying to derive the Sitter in string theory, and I personally invested a lot of effort there, and we started actually this effort of difference. So there was an enormous effort there, and nobody really succeeded. Nobody succeeded. I mean, sometimes people were making assumptions. I mean, it's usual story. We sometimes make assumptions when it's hard to compute. But really derivation didn't exist. So this is one story. And then another is this S-matrix understanding that so this happens for the good reason and stuff like this. But yeah, I would doubt that.
Okay, that's a prediction.
Yeah, it's a prediction, right? So that's what I'm saying. I think this
It
is
would be nice to check the
Exactly.
model if that's true.
Yeah, I think so.
Although I don't understand the question of anomalies because in the old, when we do phenomenology of string theory, you cancel the anomaly, you cancel the Ramon tadpole, and that comes from the anomaly. But the Navier-Schwarz and Navier-Schwarz tadpole is also there, and sometimes you cancel, sometimes you don't cancel, but it's less dangerous. So, I mean, why do you say that this is connected to the two anomalies?
You mean that? No, I just made an analogy. So because there was a question on how the low energy theory knows that the cosmological constant should be exactly zero. And I said by consistency, and I compared this to anomaly cancellation. I didn't mean string theory anomaly cancellation, generic anomaly cancellation, because anomaly also consistency requirements. And so, yeah.
Can you expand on why a big crunch is bad for DS measures? I
mean, I'm not a big crunch fan or expert, But yeah, I mean, because it has the same problem with defining asymptotic states, and I mean, yeah, I mean, I don't see how anything like asymmetrics can ever be defined on that type of background.
If there is no one, ask something. Maybe a question to all panelists. There are approaches to quantum gravity where, in principle, it doesn't even make sense to define asymptotic states. And an example is group field theory, where the elements of your theory space really are not directly related to fields. And in that case, you cannot even define Ness metrics. Maybe you can recover the concept like at low energies, but in principle, if you start from the formulation of your theory, it is not clear even if you can formulate something like that. So what do you think about this type of?
So a good example is lattice field theory for Young-Mills. You replace Young-Mills by lattice action. So what's this matrix? It's Euclidean theory, but you can still compute some observables there. So yeah, there could be some formulation of theory which you don't see how to define this matrix, but then you need to specify what are the observables, how you define the theory. At the end of the day, there will be some there will be some excitations for which there will be some consistent matrix, presumably, at least for these theories which we know.
Yeah, so I mean, I cannot really answer. I'm not familiar with specifics of those things, but the first question would be, I mean, indeed, whether they recover graviton as an effective degree of freedom. So yeah, if because again, S-metrics is the property of the deep infrared, so it touches deep infrared. So then, if in deep infrared these theories give you graviton, then definition should be usual. But if they don't give you graviton, then I don't know. Then it requires understanding what are the observables.
But then how can you say that is a theory of quantum gravity?
No, for me it would not be, because
No,
for
exactly.
me, exactly. For me, definition of quantum gravity is that this theory must be a relativistic theory of massless spin 2 operations.
That's of course, I'm not an expert of the field theory, but so one thing that Nerea was explaining us last week was that one can recover some form of Einstein equations. So you would have something like at least a metric, but I don't know in terms of a spectrum of the theory, practically from the.
Well, if you recover Einstein's equations, then you presumably recover graviton, because
in that case, there are theorems, right, that even spin 2 amplitudes give you back the same equation.
Yeah.
I mean, I would concur that if you have a model, it must be to describe some physics that maybe is non-conservative or something else, but you should have some predictions that are low energy that you, in principle, could confirm, that verify what we know about gravity.
Yeah, reproduce bending of light.
Produce what we know. I mean, I don't think we need necessarily an S matrix to define the quantum gravity. It's just that the ones we know, maybe the formulations that we know that are predictive do that. But I'm entirely happy if you have a different formulation, as long as it reproduces what we see nowadays. Has to have a spin 2 particle, has to reproduce Newtonian gravity.
No, of course.
Isn't S matrix just a natural consequence of what we call quantum mechanics in saying defining what we can observe and what we cannot observe? So it's not like a special object in that sense. We use it in field theory.
It's a natural consequence of quantum mechanics, in particular theories. There are theories that, have evolution going on into the asymptotic future, and they're not going to have S matrices.
And there are quantum theories, well-defined quantum theories that.
Well, I don't know what you mean by well-defined quantum theories. They're going to show evolution. Veneziano considered one a long, long time ago, namely lambda theta the third, without a mass term to stabilize it. And that theory, of course, decays, right? And then he asked the question whether or not if you just fold through and went ahead and put in the infrared correction, so it's going to manifest it by having the S matrix not make sense, by having it have very severe infrared divergences. He asked the question whether or not, if you just bulb through, would you get the S matrix to exist? And the answer is no, because what that theory wants really to do is to decay. It has evolution going on into the infinite future, and who's to say that we're not in, such a theory? I don't think we can. I don't think we can preclude that evolution can't go on into the infinite future, since it seems to be doing that.
I mean, yes, obviously there are quantum systems which can evolve in time, for which you can. Take two-level quantum system. You don't need really S matrix with Hamiltonian, but.
You're not going to have asymptotic states, and because it's never going to, the evolution will never turn off. You'll never have a free read.
No, we were specifically discussing relativistic theories of massless spin 2. So then you have such an example.
I would say the current universe seems to be headed in that direction. You keep saying, well, prove it, and I can't, of course. We'll never be able to prove that it's exactly a cosmological constant, or that it's. I think the relevant thing is it going to continue evolving with what do they call it? Accelerated expansion is the real issue. It's accelerated expansion that would preclude the existence of an S matrix. And
no, I was asking if you. No, I think we.
And we certainly have a spin 2 graviton, right? We're at least we're detecting the coherent states of it in the LIGO.
No, the question was if you have that's fine. But the question was, if you have a theory, well-formulated theory of massless spin 2, relativistic, in which you don't need the S matrix and stuff, and you can, then if you have such a frame.
Well, I think none of us have a well-formulated theory of anything. Like string theory only exists perturbatively. I don't think any of us have a well-defined theory of anything.
We cannot end the discussion on it.
Okay, what about the quantum electrodynamics? Does it exist according to you?
Well,
even killing quantum.
So I would say the question is, does it exist non-perturbatively? Do we have a non-perturbative definition of it? And I think the mathematical physicists would say no. I think they would say that they are not happy that there's no interacting quantum field theory in 3+1 dimensions that has been shown to rigorously exist. So I think putting that condition, do we have a mathematically well-defined theory of the thing is just too strong. Nobody has that right now. And as you point out, even for much simpler theories, which we're pretty sure exist, which we can measure in the lab to 16 decimal places.
Okay. So then this is informative to put in the universality class. What do you mean when you say theory is not well-defined? So
well, I was quoting the mathematical physicist. If you were the one who brought up well-definedness, and I think the mathematical people would say that there aren't any right now interacting 3+1 dimensional field.
We need to keep switching to a better ending. So and a better comment. Yeah.
I want to drive back to something that has been mentioned in the opening statements about this S matrix discoveries. Could you maybe elaborate? I heard it for the first time.
I wrote it.
I think you wrote it.
What I meant, and actually maybe we can ask a question also to the people working on amplitude here, because I think it's related to if we look at some perturbative regime where maybe we can compute quantities that are more connected to observable, and we try to test new predictions there. Like, what do you think? Like, how does it look like the next phase of research? Like, where do we stand in finding new signature or new principles for extending our theory of gravity? If we work in that approach, where do we stand? Can we comment on that? Can you comment on that?
You want to keep working on S matrix approach?
No. I mean, like some more perturbative approach that, for example, in the perturbative regime where I can compute amplitude, right? And I can compute observables there, and then I can have ingredients, but in a perturbative way.
Are you talking about
can-
things that will be measured or just theoretical achievements?
Because the measurements you
Both,
can
but possibly related to
you can treat gravity as an EFT, and you will hope eventually one day maybe gravitational waves observables are precise enough and we have enough of them, but statistically you can start measuring any deviations from previous GR and just start checking now the EFT corrections. So
statistics in gravitational wave
more
detection.
detection of gravitational, like many of them more precise. So it's not something that we're gonna get in 5 years. But
No, but
Yeah.
but,
that's a simple, like straightforward thing that you could get. Actually, what are the EFT corrections that GR has? Phenomenologically, I don't know if theoretically, if you care more about what are physical principles of unitarity of you need better tools, probably mathematical tools for analyzing dispersion relations when you include gravity. Because
and you mean numerical or also analytically and better understanding?
Probably both, but closer to analytic. I mean, if you can do something numeric, it's always great. And there's people that do it just full unitarity constraints on these theories, and that's great. But this also I feel like you need more of a brilliant idea on what to do next to actually have like positivity bounds when you include gravity, something that is different from what people have done nowadays. And I don't think that's going to be something numeric.
Emil, has any comment on that?
I mean, I would say the same as you. If you much statistics and good precision and observations keep improving, then maybe there could be some point where you could see some deviations and you could follow up on that. That would be interesting on a number of levels.
What deviations are you talking about due to exotic matter theories impinging on
just be that
ring down or really quantum gravitational effects?
Well, I think quantum gravitational effects are very small, but that could be maybe that the way you treat the theory and I mean, a lot of what we do as work right now is we try to use the CFT approach and really get to a one-to-one description that matches GR. But if you start seeing some deviation from GR, you have something new that could
be. These EFT terms that you think you could see in gravitational radiation signatures, they would be matter corrections or gravitational corrections like R² corrections, or
that could be one deviation. If there's high derivative couplings, you wouldn't see it in GR. You could have the type like H-bar things, but also maybe radiative effects, because when you include radiation, you have to, we are looking at these inclusive cross sections, and all the radiative effects should be consistent with the scattering process. So we have to make sure that we don't generate infinities that would invalidate the fields we approach. And we are looking basically to match everything up, so all the terms match. And
so Bremsstrahlung,
for instance.
There's one more thing that it's also important. I mean, I said just analytic stuff and just doing scattering amplitudes, but if you actually want to do the waveforms, there's a part that you cannot even reproduce, I guess, with EOV. You need numerical relativity. And if you want to test beyond GR theories, you need actually numerical relativity done for beyond GR theories. And this is in very early stages. And it's not been done for many theories. And usually it's done for theories that we, like as a theorist, don't care that much about. So that might be a big roadblock.
So this all sounds though like looking at classical effects in modified gravity theories. Is that a correct statement?
Just you can take GR as an effective field theory. It doesn't have to be called a modified gravity. It doesn't have to have an extra degree of freedom. You can just have spin to and just treat it as an effective field theory with higher derivative corrections.
If you add generic high derivative corrections, you can take most modified theories and map it.
But it's not looking at quantum gravitational effects per se. Right?
Per se, I don't think those will be measurable that easily.
They might be motivating in extra terms, but they're the thing that you're looking at could be looked at as a perturbative modified gravity theory, right?
I mean, I think you brought up QED. So if you do QED classically, I think it's not completely consistent if you look at an inclusive process. You have to actually do a QFT. So you could end up in a situation where basically GR seems to be invalidated and the QFT is more correct. But I mean, we're not there yet. But we are trying.
It's not consistent if you look at an inclusive process.
I mean, if you want to add all the additive effects, I think that there's some stuff there that is consistent when you look at it as a QFT. But if it's a classical theory, you could miss some contributions.
Yeah, just
Yeah,
mention
we can
the
have
competition
quantum
between
effects
quantum effects and
in
these
Yeah.
derivatives.
But it wouldn't be direct quantum effect like H bar, but it would be indirect things. But the basically path integral is more exact than somehow classical resolution.
In answer to the question, it seems to me the only quantum gravitational data we have is from cosmology. And there, the big thing would be if we can see the tensor power spectrum, that'll immediately tell us the scale of primordial inflation. If we can measure it well enough to get the spectral index, the tensor spectral index, then we'll be able to check the single scalar consistency relation. They say also that we're going to be able to, within the next 10 years, we'll get a factor of 5 improvement in the scalar spectral index from the ground-based telescopes in the Atacama Desert. Those are, I would say, all quantum gravitational effects. On the long run, it seems to me the thing that is really the glittering hope is 21 centimeter radiation. It's basically, does everybody know what I mean? The idea is that right now we're looking at the CMB, that's like an X-ray of the early universe. 21 centimeter radiation essentially lets us take a holograph, or what's the word? A tomograph of the universe, because the idea is that radiation, the perturbations from different parts of the volume of the universe emits something, and it's before the first light, that's all going to be 21 centimeter radiation. So by measuring its redshift and its direction that it came to us from, we can know where it came from. So we can be basically taking a tomograph of the universe instead of an X-ray of the universe. There's a vast, just unimaginably big expansion of the data set. Right now we have 10 to the 7th pixels of data. Potentially harvestable is something like 10 to the 16th pixels of data. That's enough to resolve one loop corrections. That's enough to do the gravitational analog of looking at looking at the Lamb shift.
But it's not just the amount of data, right? It's also the different scales, because CMB and 21 centimeter will be looking at different scales.
Well, okay, sure, but you're still looking at
because you're probing basically a 2-point correlation at different scales.
Sure, but you're still looking at the power spectrum.
You are still looking at the power spectrum, which you can obviously a 2-point correlation, and it's
right.
a lot of information. Also, not just because it's more data, but it's because it's more data at different scales.
That's right. You'll be able to observe it over a much longer lever arm, and see whether or not there's running of the spectral indices, things like that. And yes, I agree absolutely. So it seems to me that on the long, within the next couple of decades, that's the thing that is potentially bearing on quantum gravity.
Don't you need a tensor? Sorry, no.
Go ahead.
Don't you need a tensor mode to really capture quantum gravitational effect?
I would say no. I would say that if you count the solar system, the precision tests of the solar system as classical measurements, classical tests of general relativity, that's of course that's not gravitational radiation. That's the gravitational response to classical matter. Then you have to count the scalar power spectrum, which is the gravitational response to quantum fluctuations and whatever's driving inflation as a quantum gravitational effect.
No, but the scalar mode contains no H bar.
It does.
No, but not quantum gravitation, because
it does. The formula is, if I put in all the H bars and C's, it looks like that.
No, they of course, but I mean, the scalar mode itself is a fluctuating scalar in the background, right?
nobody knows what it is, but whatever it is that's driving inflation is presumably undergoing quantum fluctuations, because everything is.
No, I didn't.
But you want quantum gravity.
Right,
But
that's not
I'm
quantum gravity.
talking
It's
about
the
like
gravitational response to
quantum
fluctuations in the scalar, and again, if you don't count that as quantum gravity, then I will not accept the bending of light as a test of general relativity, because that's all looking at the gravitational response to classical matter.
It's more like a field in space-time. It's not really quantum gravity.
Exactly.
Yeah.
Right.
Again, do you count the radar ranging measurements, the precision solar system tests of general relativity as tests of general relativity? I would, but those are all coming from the gravitational response to classical matter.
Right.
Yeah.
This is coming from the gravitational response to quantum matter.
Yeah, but the matter
Therefore, is a test of quantum gravity.
That's a
Quantum matter.
It's testing.
Nuclear radiation is not quantum gravity.
no, that's not.
It's
What?
quantum fields on top.
No, we need
It's
this.
testing that the gravitational field is sourced by quantum fluctuations in matter.
But it's the gravitational field.
That is the basic quantum gravitational effect. That's the first thing. If you guys are worried about the ultraviolet,
No, I think
there is no ultraviolet problem in order in pure gravity. The first ultraviolet.
We need a panel on definition of quantum gravity.
Right?
You need quantum fluctuation of the matrix.
No, I think, but
That's not a
That's the gravitational response, the effect on gravity of quantum fluctuations in matter.
Right.
That's the first thing that goes wrong. That goes wrong at one loop order in most theories. And again, if you, I want to be really strong on that. If you accept this as a quantum gravitational problem, and I think most people do, you have to accept that.
I think
Data.
But it's not the
that's still
tensor. You
Exactly.
want the tensor perturbation.
I think there are probably
Just
the
take into account that perturbation is
Because
far
we think
field,
of
which is a
scalar
quantum field
perturbation
in a
as
pure
vector, which
space.
is not the intrinsic
All these like
fundamental
quantum
field.
effects of fields in a Kerbal ground. But if you would observe gravitational waves from the primordial universe.
Why you don't put that requirement on general relativity? Everybody was happy to accept the solar system tests of general relativity as tests.
Yeah.
We didn't observe the first gravitational radiation until 2015. We had indirect measurements of it from the binary pulsar spin down, but we didn't have a direct measurement until 2015. If you take exactly the same criteria that we're all happy to impose for solar system tests and for this, you have to count that as a quantum gravitational effect.
We call it quantum.
No, that's I would
matter
disagree with
equals
that
time.
definition.
Okay.
But
We'll just have to disagree.
Okay, but what about gravitational field of the Earth?
What about it?
Well, most of the mass of the Earth is quantum. It's coming from QCD.
Sure, it's
So
not
is that
fluctuating. The effect, the gravitational effect, the quantum fluctuations on it are not big as manifest on the scalar potential. So it's not a big effect. But if we could ever resolve that, yes, I would count that as a quantum gravitational effect.
But why? I mean,
That's the biggest reason. It was asked before, why is it that we have to have quantum gravity? The biggest reason is not gravitational radiation, although that's there. The biggest reason is that the Newtonian potential depends on quantum matter, and that's already going to induce problems of quantum gravity. That's what is causing this, the divergence that we see.
Very direct.
I don't know.
I mean,
quantum gravity is the spin 2, fluctuation of the spin 2. If you don't have quantum fluctuation,
I guess we just disagree on that. It seems to me that the biggest gravitational effect, the one that we saw first for the first, how many years of general relativity, almost the first century of general relativity, was the effect on the constrained fields. That's still by far the biggest effect. That's the thing that's holding us onto the floor right here. It's not gravitational radiation. Of course, the two are relativistically related to one another, but that's the biggest effect. And you all are happy counting that as a gravitational effect. That's what that is.
no, it is gravitational effect. It's just not quantum gravitational.
It is, if the thing that's holding us onto the floor is a classical gravitational effect.
So great to have different definitions of quantum gravity.
Well, so the issue is, if you have Newton's, the Newtonian potential, right, that's sourced by
Yeah, if that's quantum.
Some energy density, right? Question is, do you source it by this, or do you source it by the energy density operator? This is saying that we're sourcing it by the energy density operator, that some component of the gravitational field, this is surely a gravitational field, is becoming quantum, not because of gravitational radiation, but just because it depends upon the quantum operators that are sourcing it.
No,
It's not
you
the
don't need
transfer
to quantize
spectrums.
gravity. You don't need to quantize gravity.
I think you're making a distinction that we do not make anywhere else. And again, I will point to this. You all point to this as a problem in quantum gravity, right? That's where the first divergences occur in quantum gravity. This is not coming from graviton loops. Graviton loops at one loop order are finite, at least on shell. This is coming from the gravitational response to matter. That's exactly the same thing that's being measured there.
Maybe to reconcile these 2 points of view, indeed, there is no known framework where you keep gravity classical and have quantum matter. So if you write some path integral, you will run into various issues. But that framework is approximation, because you still need to quantize everything.
Well, I actually agree with you. There's no good framework where you have gravity driven by classical matter. Again, I get asked to referee these papers by people who have exotic points of view, shall we say, and they come up with very, very complicated ways of trying to drive gravity by classical matter, and I lose patience in trying to find the error. So I can't say that they can't do it, but I actually agree completely with you. It's the obvious thing. I think somebody before mentioned Occam's razor, and the simplest explanation is just that metric is being driven by quantum matter, and that's a quantum gravitational effect, just like that is.
But only if it fluctuates. I mean, if you can derive things from a path integral, what makes the difference is what are you integrating over. If you're also integrating over graviton fluctuations, then you're doing quantum gravity. If you're keeping the gravity fixed and you're integrating over quantum matter, that is just
okay. So let's take the same restriction on classical gravitational effects, right? I claim that almost everything in the solar system is explained by the constrained degree of freedom that doesn't include any gravitational radiation. If we just turned gravitational radiation off, if we took the lever and pulled it down and killed all gravitational radiation so that the LIGO detector suddenly turns off and they don't detect anything ever again, you would still get almost all the solar system effects. And the constraint that you're imposing is to say that we will not count those as tests of general relativity. I think that's...
No, but this probably was ruled out, just not to have spin 2 in the game.
Yeah, I mean, it seems to me that if you have these things, then relativistic extensions of them certainly do induce gravitational radiation.
It's part of the story, but not the full story. We need to agree on that.
Oh, I absolutely agree. Look, I passionately want to. I mean, okay. I have a good bit of my requirement I would give if somebody could measure the tensor power spectrum. It will tell us so many things. It will tell us what the scale of inflation is. I mean, it would test if we could measure the tensor spectral index, it would tell us whether it's single scalar models. Yes, I emphatically want that. But I do think this by itself is already a quantum gravitational effect, and it's the first our species has ever got. And it's an awesome thing. It blows me away. I never thought when I was your age, I never thought I would live to see it. I actually wrote it in my thesis that I would never see it. But it's
the right enthusiasm to be able to drive towards the conclusion. But it was mentioned by Renata also on Monday that cosmological data are coming over the next years. And although it seemed you were a little bit like not excited of the fact that there's a lot of things to compute and there's many things that have not been computed yet, that's actually quite exciting from the research point of view. And so hopefully, I think we're heading towards an era where this workshop 10 years from now will have probably a different answers to this panel and a different discussion. So in that spirit, I would like to thank again all the panelists for interesting discussions. And yes.